Hello students, this video is designed to help with the 4th Regents Review session that I had on proofs. If you haven't already done so, I gave out a packet in class, and the packet looks sort of like this. The packet has 12 different proofs for you to try. As you can imagine, that's a lot of proofs to go over in a 15-minute video, so I'm going to show them and try to highlight the main points, but I'm not going to go through them exactly step by step. So take a minute, pause the video if you haven't already done so, try to answer these questions, and then come back when you're done. Alright, let's take a look at the first proof. This is a one way of this proof being proved. It's not the only method by any means. One thing that you should remember about this proof is that it's asking you to prove that two triangles are congruent. So we're going to use one of the 5 methods that we've learned about this here. Side, 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 angle, 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 side, or hypotenuse leg. No right angles here, so it's not going to be hypotenuse leg. Definition of bisector here, they wrote definition of angle bisector, but you're okay to say bisector because they're using the word bisects here. The reflexive property of congruence, we could just write as reflexive property, that's no big deal, and Sas Postulate should be fine for that. They could have gone further to say, oh, for example, SQ is congruent to TQ because of CPCTC, but that's not what this question was asking us to do. Alright, moving on to proof number 2. This was an example of a proof that requires two congruent angles or two congruent triangles before you prove something else. They gave us these two congruent sides, and we know that this third side AD is congruent to itself, so we're able to use side, side, side congruence postulate, or just side, side, side postulate, to prove those two triangles are congruent. Once we know the triangles are congruent, then we know that their corresponding sides are congruent, or their corresponding parts are congruent, I should say, and then we can use the definition of angle bisector to prove that they're bisected. For proof number 3, this is a very short proof. We were given a shape that we don't even know if it's a parallelogram or not. So we can't use any of those definitions of parallelograms. We can't use like opposite sides are parallel or opposite angles are congruent, anything like that. But we were given enough information. We were given that these two parallel lines and these two congruent lines exist in the shape. So we were able to use alternate interior angles to prove that these two angles are congruent. That XZ is congruent to XZ. Sometimes you'll see this as XZ is congruent to ZX. It doesn't really matter what the order is. Typically, you'll have it in alphabetical order. But in any event, once we have those pieces of information written down, we have a side that's congruent. This side is congruent to this side. We were able to prove that WXZ, this angle, is congruent to this angle down here. And we were also able to prove that this side is congruent to itself. So we can clearly see side, angle, side. That's how we got Sas Postulate. Moving on to proof 4, Pgram stands for parallelogram. Now we know a lot of stuff about this shape. The definition of parallelogram gives us that AB is parallel to DC. That's this line and this line, and we know that parallelograms have opposite sides that are parallel. We also know that opposite sides of a parallelogram aren't just parallel, they're also congruent. We were able to use alternate interior angles once you knew that they were parallel. We were able to prove triangles are congruent, and then we were able to use CPCTC to figure out that the parts of those congruent triangles are congruent. Once again, in this type of proof, we're trying to first prove that the triangles are congruent in some way, and then we're trying to find their parts that are congruent. For proof number 5, we were trying to prove that it's a parallelogram. So if you try to start by saying that AD is congruent to BC, for example, you weren't allowed to do that. We don't know that yet because we don't have the definition of a parallelogram as a given. We're trying to prove it. So in order to prove that something is a parallelogram, there's a number of different ways to do it. They went about it in this way. They were trying to prove that BC is parallel to AD, that's BC, this one, is parallel to AD, that's this one. And then they went about proving that AB is parallel to DC. That's sufficient to prove that this shape is a parallelogram. You could have done other things though. For example, AC is congruent to EC, ED is congruent to EB. That means that these two diagonals bisect each other. So if you had stated that E is the midpoint of those two diagonals and then said that it is a parallelogram because the diagonals bisect each other, I wouldn't have been mad. I would have been impressed. Proof number 6, a very simple diagram. It's given to us that angle 2 is congruent to angle 1. This was a use of the transitive property. Transitive property says this. I know that angle 2 is congruent to angle 1. So angle 1 is congruent to angle 2. I also know that that same angle 1 is congruent to angle 3. Well, if angle 2 is congruent to angle 1, and angle 3 is also congruent to angle 1, then these two angles, angle 2 and angle 3, must be congruent to each other. That simple idea that if two things are equal and other two things are equal, then those other two things are equal to those other two things, a bad way to say it. That's an easy way to prove the transitive property, or an easier way to say that would be transitive property. Moving on to question number 7, proof number 7. It was given to us that it's a trapezoid, and a trapezoid has one pair of parallel sides, and the other pair of sides are not parallel. In this case, we know that it is an isosceles trapezoid because we're given that AD is congruent to BC. And we're able to use that to our advantage by saying, well, if these two sides are the same, then these two base angles are also the same. That means that ADC is congruent to BCD. That's this step here. Later on, we were able to prove that the two triangles are congruent by SAS. You could, of course, said Sas Postulate. And then here, AC is congruent to BD. That's this line and this line based on CPCTC. One way that I tried to show students how to do this is by drawing these as separate triangles, and I'll show you what I mean. All right, you can sort of see what I did here. I drew these two triangles, and then I separated them. You can also mark up the diagram. I know that AD is here. I also know that BC is here, and we know that they're congruent to each other. We know that DC is congruent to itself, so we're able to make this X mark for reflexive property. And then we were able to find out by using the isosceles trapezoid definition that this angle is congruent to this angle. So if you redraw the triangles, you can see pretty clearly what's going on in this problem. We're using Sas Postulate. It's not that difficult to see once you redraw the triangle. So my urgent message to you would be to redraw the triangles anytime you're trying to look at two overlapping triangles and trying to figure out what their relationship is. All right, for proof number 8, it's given to us that it's a parallelogram. Thank you very much for that because that's super useful. Once we know it's a parallelogram, there's a lot of different ways to prove that it's a rhombus. In order to figure out whether it's a rhombus, we could say that the sides are equal to each other, all sides are equal to each other. We could also say that the diagonals are perpendicular to each other, and we can also say that the diagonals bisect the angles. So their choice was to prove that all sides are congruent to each other. That's here. Once we prove that all sides are congruent to each other, it's basically a rhombus. We know this, we haven't proved that this is a square or not a square, and that's irrelevant because as long as we prove that it's a rhombus, we're good to go. Proof number 9 gives an example of the subtraction postulate and the substitution postulate. It's very, very straightforward and sometimes misconstrued by students, so let me try to walk you through it. I have BD, which is here. That's this entire line here. That's BD is congruent to this entire line here, which is CE. What I'm trying to say to you, what I'm trying to build up here is that, well, CD is congruent to itself. This little piece is congruent to itself. And if I take that little piece away from BC, and if I take that little piece away from CE, then the resultant shapes, the resultant lines, this line here and this line here, should be equal to each other. I know that BD is congruent to CE. I know that if I take away the same exact amount from both of those things, they remain equal. So that's the subtraction postulate. And then substitution postulate to say, well, instead of saying BD minus CD, I know that BD minus CD is equal to BC. Substitution postulate just takes two things that are a little bit too complicated and makes them a little bit simpler. All right, moving on to proof number 10. This was a weird proof. I don't think that you'll see this type of proof on the Regents exam. It's included for completion's sake. We're trying to prove that line Q is perpendicular to line A. So the first thing we have to do is prove that line P is perpendicular to line A. It seems to make perfect sense to me because these two angles are congruent to each other. It says that here. And they're also supplementary. So this must be 90 and this must be 90 in order for them to equal 180. Well, if this line is perpendicular to this line, then any line that's parallel to P is also going to be perpendicular to this line. That's what it says here. Parallel lines are perpendicular to the same line. There are other ways to say it, but this is probably the most straightforward way to say it. In proof 11, we're given two triangles. Normally, I would draw these separately, but they're basically separate already. It's given to us that angle K is congruent to angle M, and it also is given to us that L is the midpoint of KM, which brings us to this line being congruent to this line. Now be careful, it says midpoint here. So I don't want you to write definition of bisector here. Whenever it gives you the term midpoint, you're going to say definition of midpoint. You're not going to say definition of bisector. That's a fight that I've been fighting all year with you students. Then I know that PLM, that's this angle here, I'm going to make two arcs because I already have one arc here, is congruent to angle JLK. I apologize for that. That's JLK. And I know that these two are congruent to each other because of vertical angles. Once I have that, I have an angle, a side, and an angle. That's angle, side, angle postulate. And finally, proof number 12. There were a couple of different ways to do this. There was a cute way involving the fact that BD is an altitude of this triangle. And we were able to prove that because if a line from one vertex to the base is perpendicular to the base and also bisects that base, then it must be an isosceles triangle. That's a little cute. I don't necessarily want you to be too cute. Just use what you know. Definition of perpendicular, you definitely know what that means. Right angles being congruent, you definitely know that all 90-degree angles are congruent. Reflexive property just means the same thing is congruent to the same thing. Sas postulate is very straightforward because we know that we're looking at side angle side being congruent. Let me mark that on the diagram here. Here's our statements on the diagram. Hopefully it's a little bit more straightforward to see. Side angle side is congruent to side angle side. And then we're proving that these two angles are congruent to each other because of CPCTC. Here's a quick hint for you. I am going to be testing you on this idea, this concept in class very soon. So keep in mind that this proof is going to be a very important proof on that exam. A very, very important proof. So if you go home and if you memorize one proof, if you memorize how one proof is done, you should probably memorize this one. Alright, this was a video trying to help you with the Regents Review packet that I gave out in class about proofs. Please make sure that you understand how the proofs are done. Please make sure you memorize those different postulates and theorems. And overall, good luck studying.